So in our quest to use the surface area strategy to find the surface area of a sphere, we can describe a sphere, or at least a portion of a sphere, as the graph of a function of x and y by solving x squared plus y squared plus z squared equals r squared, solving it for z. If we take the positive square root, z equals square root of r squared minus x squared minus y squared, then we're getting the top hemisphere, right? Because the square root is always giving us something non-negative. And so then if we apply our surface area of a graph formula from up here, we need to take the square root of the sum of the squares of the partial derivatives of our function plus 1, and then try to integrate that where x and y range over the appropriate ranges of x and y. So the partial derivatives of our function are respectively minus x and minus y over the square root of r squared minus x squared minus y squared, so that when we add the sum of their squares plus 1, we do some fraction arithmetic, and we end up getting r squared over r squared minus x squared minus y squared. And so taking the square root of that, I think I also have a typo here, that the numerator ought to be just r, right? R over the square root of r squared minus x squared minus y squared ends up being the thing that we go to integrate. There. And the trick of this part, the sort of the sly difficulty, was that we had to figure out what range of x and y are necessary to parameterize that top half of the hemisphere. And so we, in order to get that top half of the hemisphere, we need to let x and y range over the circle, the disk of radius r in the xy plane. And so now we have a two-dimensional tape measurement issue that we need to resolve, and we resolve that issue by solving the equation for the circle of radius r in the xy plane, solving it for y, and thereby getting a type 1 description of this region. So this would range from minus the square root of r squared minus x squared on the bottom side, up to positive square root of r squared minus x squared on the top side. And then the left and right hand limits, once we squash that circle of radius r down onto the x-axis, then the left and right hand limits end up being from minus r to plus r. And so this ends up being our tape measuring for the range of x and y that are appropriate for the integral that we're setting up. And so that's where you got this iterated integral, the integral from minus radical r squared minus x squared to plus r squared, radical r squared minus x squared, and then the integral from minus r to r, so dy dx. So this integral is nasty to say the least, right? This is sort of typical of what happens when we do set up surface area integrals, right? Is we get the square root of a bunch of junk that has like pluses and minuses in it, and it's just finding an antiderivative for that thing is kind of nightmarish. If we wanted to do it as it's directly written, we would probably end up reaching for a trigonometric substitution that turns this into an inverse trig kind of integral. It's probably an arc sine or something, awful like that if we try to find an antiderivative of that thing with respect to y. And then we would have to plug in y equals square root of r squared minus x squared, y equals minus the square root of r squared minus x squared. And so, it sort of almost takes my breath away, just like how I don't want to think about that right now. It just seems way too nasty. So there is another option available to us. Right? Anytime we have an integral in rectangular coordinates that looks kind of messy, but it looks like we're probably doing some stuff that is better described with a radius and an angle instead of an x-coordinate and a y-coordinate, we should think about converting to polar coordinates. So that's what I want us to do next, is to take this integral that we just set up and this region that we just tape measured, and instead of using x and y coordinates to express it, use polar coordinates to express it. Not only is that going to give us some nicer limits of integration, when you transform the integrand and the area element dy dx, I think you'll find that the integral that we end up with, the antiderivative problem that we end up with, is actually much more doable than the one that we have here. So let's get started on converting this into polar coordinates and rendering it a possible integral. So converting this into polar coordinates required us to both use the polar coordinate transformations to change the integrand. So r squared minus x squared minus y squared turned into big R squared minus the polar coordinate little r squared. And our area element, dy dx, turns into r dr d theta. And then we also had to go back and re-tape measure our region. Right? And when we re-tape measure our region, we end up getting constant bounds in polar coordinates, which is another real virtue of using polar coordinates for a problem like this. Because to parameterize the disk of radius r in polar coordinates, we'll let r range from 0 to capital R, the radius of our disk, and we'll let theta range from 0 to 2 pi. And that will tape measure, that parameterizes this disk for us. So our new integral that we get has constant limits of integration. Its integrand depends only on r and not on theta, so this is going to be one of those integrals that we can break apart into a product of two integrals when we go to evaluate it. I'm just going to put that observation in here to save us a little bit of time when we go to evaluate it. But then something else happens in this process. There's another virtue of what has happened here. We're going to have the integral from 0 to capital R, from 0 to capital R, of the function of r, which is on the inside. So we'll call that big R times little r over the square root of big R squared minus little r squared. That's the integral with respect to r. Oops. And then we're going to be able to multiply that integral by the integral of the theta dependence, but there is no theta dependence, right? It's the integral from 0 to 2 pi of 1 with respect to theta. So, because the integrand depended only on r and not on theta, it's a constant with respect to the theta integral. So we can just pull it out and decouple these integrals because they have constant bounds as well. Also, notice that this integration with respect to r has picked up this extra factor of little r in the process when we did the polar coordinate transformation. Let's take the capital R, which is a constant, and just factor it outside of our integral so that we can focus on what matters the most. And what it shows us is that now we need to find an antiderivative not for 1 over the square root of r squared minus something, but for r over the square root of r squared minus little r squared. So now we have an integrand that we can actually find an antiderivative for without doing any fancy stuff. The most that we would need probably is a u substitution, rather than reaching for inverse trigonometry and all kinds of other scary stuff that we would have had to do if we tried to do this in rectangular coordinates. So go ahead and do that u substitution, dust that off. Probably haven't had to think about that for a while. And that'll finish up this integration for us. So once we made the polar coordinate substitution, our limits of integration became constants, because in polar coordinates, our circle, or disk of radius r, rather, can be described using constant bounds on the polar coordinates r and theta. So that was piece of good news number 1. Piece of good news number 2 is that the integrand simplifies into a function only of r and not of theta. So this integrand is what we call a radially symmetric function, right? Every ray that we draw from the origin of any angle is going to see the same cross section, shaped like r over the square root of r squared minus little r squared. And so we ended up with an integral where the integrand depended only on the r variable and not the theta variable, and our limits of integration were constants. And so what that lets us do is break it apart into a product of two integrals, and do the theta integral separately, and do the r integral separately, and multiply the results. The theta integral from 0 to 2 pi of 1 just gives us 2 pi. And the r integral, which looked impossible to do, we would have needed inverse trigonometry to do it if we used the original rectangular coordinates. In the polar coordinates, this extra factor of r that came with our area element conversion comes in to save the day, because it allows us to use a u substitution to find an antiderivative for this. So u equals big R squared minus little r squared lets us transform this into the integral from r squared to 0 of negative a half over the square root of u. And then that's straightforward evaluation of an antiderivative evaluated from r squared to 0 is equal to r. And so in total, the surface area for the top half of the sphere that we found is r times 2 pi r squared. And if that's the top half of the sphere, then the whole sphere is going to be twice as much, or 4 pi r squared, which is again the formula that we received in high school geometry.